We've seen that the dot product lets us do a lot of things in Rn that we don't really have any corresponding tricks for in other vector spaces. Things like checking when vectors are perpendicular, or doing the Gram-Schmidt process to get an orthonormal basis for the vector space. So maybe what we should do is identify some properties of the dot product that make it work the way it does, so that we could identify similar things in other vector spaces. So here are the properties of the dot product that sort of are the basics that make it work the way it does. So one is that the dot product is commutative, or another way to say that is that it's symmetric. So it doesn't matter which order you do the dot product, you get the same real number either way. Another thing about the dot product is that it's so-called bilinear. So if you have a linear combination on the left factor of the dot product, then you can distribute it and move the scalars outside. A and B here are supposed to be denoting scalars. So you can distribute the dot product leftwards, and also you can distribute the dot product rightwards. Of course, because the dot product is symmetric, I don't really need to say these two things separately, but I'm just writing them both down for completeness. And then the last thing that makes the dot product significant is that if you take a dot product of a vector with itself, you always get something greater than or equal to 0. So in the particular case of the dot product, this is sort of connected with why the dot product gives us lengths of vectors. But in general, besides the fact that the v dot v actually gives us the square of the length of a vector, just at a more basic level, v dot v is greater than or equal to 0, and it's equal to 0 only when v itself is the 0 vector. This is called being positive definite for no particular reason. Well, all of these properties are properties that we could identify in any vector space. If we had a product, some operation that took two vectors from that vector space and gave us a real number, we could check if that operation satisfies these three things, or these three conditions. And if it does, then somehow it can play the role that the dot product plays in Rn. So we'll call this sort of operation an inner product. So an inner product on a vector space is an operation that takes two vectors and that associates with each pair of vectors a scalar, which we'll write this way with angle brackets. So, and I guess we'll pronounce this U product, inner product with V. To count as an inner product, this operation has to be symmetric, bilinear, and positive definite, just like the dot product. If we do have a vector space equipped with one of these inner products, we'll call it an inner product space, or just a vector space with inner product. So let's have a look at some examples of inner products on familiar vector spaces. Well, for one thing, Rn has more inner products on it than just the dot product. Of course, the dot product is kind of the most important one for various geometric reasons, but there are other dot products on Rn. Just as an example, on R2, let's check that this defines an inner product. So we have to check these three things. Well, this first one, clearly this is symmetric, because if you did this product the other way, you would just get 3v1u1 plus 2v2u2. But these products here, this is multiplication of real numbers, and so it doesn't matter what order you do these in. And so these are equal to each other. So that's symmetry taken care of. To see that this is bilinear, I guess we're going to need another vector. Let's call it W, so W1, W2. And to check that this operation is bilinear, we just grind through the writing down, oops, not U1, just U. Just grind through writing down this whole mess. Right? If we actually calculate the entries of AU plus BV, the first entry of AU times BV is AU1 plus BV1, and then multiply that by the first entry of the other part of this product, W, plus, and then for the second components, we get a, oh, I'm missing a 3 here. I need a 3 out front because that's the definition of this product. And then I need a 2 here. 2AU2 plus BV2 times W2. And then, if we multiply all this out and then group things appropriately, we get A times 3U1 W1 plus 2U2 W2 plus, and then for the parts with V's in them, we get B times 3V1 W1 plus 2V2 W2. And of course, this is A times the inner product of U and W plus B times, angle bracket, times B plus B times the inner product of V and W. Okay, so that verifies that it is indeed bilinear. And then finally, for a positive definite, let's just take the inner product of V with itself and see what we get. We get 3V1 squared plus plus 2V2 squared. And we want to know, is this always greater than or equal to 0? Well, 3 and 2 are both positive numbers. V1 squared and V2 squared are not negative, right? They have to be greater than or equal to 0 because they're real numbers squared. And so this whole thing definitely is greater than or equal to 0. So that takes care of this part. But what about the second part? How could this number here be equal to 0? Well, it's equal to 0 if and only if V1 is equal to 0 and V2 is equal to 0. In other words, if and only if V is equal to the 0 vector. And that's the second part of being positive definite. So this is an inner product. You can see that we can choose any coefficients here as long as they're positive, and we will get an inner product using this particular combination of U and V. So really, there are lots of inner products on R2, and by extension, of course, there are lots of inner products on Rn for any n. Although again, the dot product is the important one, the most important one, typically. All right, for another example, let's have a look at this possible inner product. So this is very similar to the dot product, except you can see I've actually switched the order of which component of U gets multiplied by which component of V. So let's check our 3 conditions to see if this is an inner product. So first let's check symmetry. So what is V inner product with U? So that's going to be V1 U2 plus V2 U1. Is that equal to this up here? Yes, it is. So this is symmetric. Is it bilinear? So if we have AU plus BV, inner product with W, what does this give us? This gives us, let's see, AU1 plus BV1 times W2 plus AU2 plus BV1 times, BV2 times W1. Then when we multiply all of these out and then group them appropriately, we get, let's see, A times U1 W2 plus U2 W1 plus B times V1 W2 plus V2 W1. And this is indeed A times U inner product W plus B times V inner product W. So this is bilinear. Now let's check positive definite. Okay, so we have to think about the inner product of V with itself. So the inner product of V with itself is going to be V1 v2 plus v2 v1. So this is just 2 v1 v2. And is this always greater than or equal to 0? Well, seems very suspicious because nothing is squared. So what's guaranteeing that this whole thing should be positive? With that in mind, it's easy to come up with a counterexample. So if we take the inner product of, say, how about -1 and 1 with itself. Or sorry, I shouldn't say inner product because we don't know if it's an inner product, and we're seeing now that it's not. What we get here is, right, 2 times -1 times +1. That's -2. This is not positive definite. So this whole thing isn't actually an inner product. So it's some kind of product, but it's not an inner product. For a final example, on the vector space Pn, so remember this is polynomials of degree less than or equal to n, let's fix k distinct real numbers. So these x values we're fixing once and for all, so we aren't allowed to change them. And we're going to define a product of polynomials by evaluating each polynomial at each of these x values, and then sort of multiply corresponding outputs, and then adding them up. Right? So is this an inner product? Well, is it symmetric? Well, you can see if we just switch the location of each p and q, we get the same thing, so yes. Is it bilinear? So this time I won't write out the proof of being bilinear, but you can convince yourself probably that it is if you just write out what this whole mess is, a times p of x plus b times q of x, inner product with some other polynomial h of x. You can run through the proof exactly like I did in the previous examples and group things accordingly, and you'll see that it is bilinear. Okay, so now let's check positive definiteness. So let's take this product of p with itself and think about if it has to be greater than or equal to 0 or not. So this is going to be px1 times px1 plus, and so on, all the way up to the last x value. So this is px sub k times px sub k. Whoops, I got my parenthesis in the wrong place there. Okay. And now things are looking pretty good because this is p of x1 squared plus ... plus up to p of x sub k squared. And is this always greater than or equal to 0? Well, each term in this sum is squared. Each term is a real number, so each term is a number that's greater than or equal to 0. So yes, this is always greater than or equal to 0. So now we have to check, is the inner product of p with itself equal to 0 only for the 0 polynomial, that is the polynomial p of x equals 0. So what we have to ask ourselves is, for a polynomial, is it possible that all of these things add up to 0? Well, all of these things add up to 0 only if each one individually is 0, right? So if the inner product of p with itself is 0, then we would have to have p of x1 equal to 0, p of x2 equal to 0, and so on, all the way down to p of x sub k equal to 0. Is it possible that a non-zero polynomial could have this many inputs that produce 0 as an output? Well, here we have to be a little bit careful. How many zeros, how many roots can a polynomial in Pn have? Well, an n, right, Pn is polynomials of degree less than or equal to n. So polynomials in Pn could have as many as n zeros, right? And still be non-zero. So if we want this to happen only for the zero polynomial, we need to have enough items in our list here so that there's more than n of them, right? Because if there were as many as exactly n of them, it is possible for an n-degree polynomial to have n distinct roots and not be the zero polynomial. So for this whole thing to still be positive definite, we need k to be at least n plus 1. Right? Just n isn't good enough because it's possible for an n-degree polynomial to have n roots and still be a non-zero polynomial. So we need n plus 1 x values in our list way up here to begin with. Okay. And in this case, then if we have this many x values in our list, then this inner product or this product is 0 if and only if the polynomial itself is 0. And in this case, we do have positive definiteness. Okay, so in Rn, there are lots of inner products, right? Picking any real numbers here will do. But switching the components of the vectors around in Rn typically does not produce an inner product. On the space of polynomials, there are also lots of inner products, right? They all, you can get other inner products just by sticking positive numbers in here as multiples, but we do have to have a list of x values long enough so that we get positive definiteness.